Hi everyone. This week we will continue our journey into polynomials. Last time we talked about quadratic, which is degree 2 polynomials, and how they can be used for modeling certain scenarios, what they look like. That is, they look like a parabola going upwards or downwards. And today we are going to extend that to higher degrees of polynomial. So this is what we already know. Linear is usually characterized by mx plus c, where m is the slope and c is the intercept on the y-axis. So that any line, as you change m, right, change m, the line rotates. As you change c, the line goes up and down. Okay, so there are two parameters that you can control. Then the next thing we saw is a quadratic, and the quadratic can look something like that. And it has two basic shapes depending on whether a is positive or a is negative. Okay, so depending on that, there are two possible shapes, and as a result of these possible shapes, you have either a minimum or a maximum point. And because of the nature of squaring, these are symmetrical because they are squares. So let's take a step further and go 1 degree higher, which is x cubed. Now the easiest way to sort of understand it is to pick some values. So when x is 0, this is 0 cubed is 0. When x is 1, 1 cubed is 1. When x is 2, 2 cubed is 8. When x is 3, 3 cubed is 27. So this is increasing pretty quickly. So let's look at negative numbers now. A negative 1 cubed is actually back to negative 1, because negative 1 times negative 1 is positive 1, and then that times negative 1 is negative 1. Negative 2 cubed is negative 8, and negative 3 cubed is negative 27. So what you notice is these are the same numbers. They only differ in being plus or minus. That's because when you cube, you're multiplying something that is negative 3 times, right? So if it's 3 times, it goes back to being negative instead of positive. Which means that if you were to plot this, for positive values of x, it increases really fast, and for negative values of x, it goes down. So that would be a typical shape for y equals x cubed, saying that x, as x increases, y increases, and as x decreases, y decreases, right? Meaning it becomes more and more and more negative. So that is the shape. Now what is the fundamental difference between these? Y equals x squared looks like that, and y equals x cubed looks like that. But what is the fundamental difference? The fundamental difference here is that this is x times x, right? Which means positive times positive gives me positive, and negative times negative also gives me a positive. But this is x times x times x. So it's 3 multiplications. So here, positive times positive times positive gives me positive. Negative times negative times negative gives me negative. So that is the fundamental difference in the shape. Because both of these give positive, you have a symmetric shape. They go up together. And here, one gives positive and the other gives a negative. They go in 2 different directions, right? And this is a consequence of how many x's you are multiplying together. right? Now this happens because there's an even number of x's being multiplied, and this happens because there's an odd number of x's being multiplied. So that when you have an odd number of negative things multiplying, your final result will be negative. Which means that we can generalize the shape of these graphs for different values of n. So if n is even, the shape is going to look like that. If n is odd, then the shape is going to look like that. Of course, there is the possibility of this, and in the same way, there is a possibility of this. We will talk about that in more details in the videos and the discussion that follows this. But in general, so if you have an even exponent, then it is symmetric. And if you have an odd exponent, then if the positive goes to positive infinity, the negative goes to negative infinity. So they are always opposing in sign. So let's try to plot. Now recall graph transformations, right? So we will use graph transformations. First one simply goes from x cubed to negative x cubed. Okay, so x cubed is that negative x cubed means you're flipping the output, right? So you just reflect along the x-axis. And in fact, in this case, you can also reflect around the y-axis, and it gives you the same result. The second one goes from x to the 4 to x minus 2 to the 4. So x to the 4, because of an even power, looks like that. And then x minus 2, right, means you're moving it 2 units to the right, and that is going to be x minus 2 to the 4. And this point is precisely 2, 0. The last one you have, there's going to be three steps here. You start with x to the 4, then you scale it and invert it, and then you add 4, right? So what does that mean? Graphically, now x to the 5 means it's odd, so that's the shape. And then I stretch it and I also invert it, so maybe it just becomes like that, steeper. And then finally, that's x to the 5, negative 2x to the 5. Adding 4 means I raise it up by 4 units. So I'm no longer crossing over at 0, I'm crossing over at some other place. Right? The output is 4. So now it looks something like that. So this means that now we basically have the ability to draw any of these polynomials based on two information, based on how they behave according to odd or evenness of the exponent, and also according to graph transformations that we have learned so far. One more thing, if we go back here, we said that these are the two possibilities, right? Similarly, you have these two possibilities. Now there's a way to talk about these things, which is called end behavior. And what is that? What it says is, for a polynomial, say p of x, what, or y equals p of x, what happens to y as x becomes a large positive number, and what happens to y as x becomes a large negative number. Okay, so for example, if I give you this graph, then you can say that as x becomes large, your output sort of becomes large, right? Y also a large positive number. And as x is a large negative number, your y is also a large negative number. So that's called endpoint behavior. Now if I have a graph like that, then as x a large positive, y large positive. Oh, this should be positive here. As x large negative, y also large negative. So these are the two possible. Again, over here, the first one is an even powered case. So it makes sense that no matter if your input is positive or negative, your output is always positive. And the second one, they will have different behavior because it's odd powered. One last thing to discuss in this, actually I'm going to stop this video here, and in the next video we continue the discussion on endpoint behavior, and we will find that actually just from what we know, we can already sort of define all the possible endpoint behaviors, meaning that there's a very limited number of combinations that these polynomial graphs can take. So we're going to look at that and then look at some more examples. That's it for this video. Thank you.